Almost ready to start. I'm doing some different things with my camera here. So I've got my green screen so I can be a part of the talk today. And grab that. Okay. If anybody wants to hit me up on the top chat, let me know if the volume is good. Like I said, I've had a little echoey because I've had two microphones going, but I think I've got it all worked out now. All right. All right. So I've got 3:30, so let's go ahead and get started. This is the second time I've given this lecture today, which I'm glad because it's given me the opportunity to do it a little bit better this afternoon than I did this morning. So the volume sounds good. Thank you so much. I really appreciate you hitting me back there. Sorry about that. Need a drink here. My fourth lecture today. Yeah, gets a little tiring here. But at any rate, this lecture hopefully will be a little bit better than this morning. I kind of cleaned up the slides a little bit, chopped them up, same information, but I'll just post this one only and learn and make only this one available for us on the web. So this will hopefully be the better one. So we're talking about bones, and we've talked about the structure of bones, and today we're basically going to focus on bone formation, and specifically we're going to look at ossification of bones, how they become actually hard. And for those of you in my AMP class, this will be section 6.3. And I'm not going to cover anything else today because we're going to continue on with bones again next week. Okay. Camera. Okay, good. I'm glad everything's working with the camera and the volume. Thank you so much. Okay, I've had some bad weather out here. There's a lot of snow where I'm at, so I've been getting a little bit jumpy video. If it starts jumping around, let me know. I can repeat stuff again for us, so that's not a big deal. Okay, so I've got everybody's, I can see your top chats there, so awesome. Thank you. So, as you guys know me, before I dive into bone ossification, there's this really cool evolutionary connection. You see, I keep telling you, we're modified fish, right? I'm not kidding here. So our ancestors were, of course, the chordates, which are evolved into vertebrates some 500 million years ago. There were fish in the seas, over 430 million years ago. And our ancestors were these cartilaginous fish. They had cartilage. They didn't have ossified bones. We know them today as chondrichthyes. Chondrichthyes, right? Chondro for the cartilage, and ichthyes meaning fish, so they are the cartilaginous fish. And the earliest ones that we know about were probably over 430 million years ago. Now, here's what's cool. About 420 million years ago, evolving from those cartilaginous fish were the earliest bony fish known as osteichthyes. Osteo, there it is, bone. Ichthyes means fish. So osteichthyes means bony fish, and the first ones were around 420 million years ago. So interestingly, when we talk about bone ossification, we're actually starting out with a cartilaginous model, and then we replace the cartilage with bone. And in fact, we have chondrocytes that actually redifferentiate into an osteogenic cell and then become an osteoblast. So wow, even in our own development, we can see the remnants of our really ancient fish ancestors dating back 400 plus million years. Okay, now let me pull this over here so I can see this. Got a few more of you joining in. All right. So, here we go. Osteogenesis. We know the roots of these words here. Osteo just means bone. Genesis, of course, means origin of the bone. And, of course, we start off with primary bone, which isn't quite as hard, and that will eventually get replaced by the secondary bone in development. Now, this osteogenesis, which is also ossification, okay? There are two different mechanisms that we're going to talk about today. The first one is intramembranous ossification. And the second one is the endochondral ossification. Okay? So let's take a closer look. Intramembranous ossification. Let's break that word down. Intramembranous. Intra means within. Membrane means we're within a membrane. Ossification. So what happens here is that there is connective tissue, cartilage, that forms a membrane. And that forms the model. And we actually call this a mesenchymal membrane made up of, this is going to be easy, mesenchymal cells, right? So our mesenchymal membrane is laid down by our mesenchymal cells, and that forms a model that will eventually become ossified through intramembranous ossification. And this happens in our skull, right? And in our clavicles. Okay, now of course, the other one being the endochondral ossification, that occurs basically neck down. All the other bones in our body do endochondral ossification. So here's how it happens. Intramembranous ossification. Basically, you start off with this mesenchymal membrane with the mesenchyme cells. Now basically, we start at a primary ossification center. Primary just means first, right? Okay, here's what happens in this primary ossification center. Basically, I thought somebody was up there behind me. My kids are here and my dogs are around, but I thought I had the door closed. Okay, back to this. You have these mesenchymal cells in this primary ossification center. Those mesenchymal cells, they differentiate or change into what is called an osteogenic cell. Osteo means bone, genic means like genesis, origins, and of course osteogenic cells will differentiate into an osteoblast. Now, just as a side step here, we know that we have about 200 different types of cells in our body, 200 different types, and they are basically all genetically identical to each other. They have the same genes. Even a nerve cell, a muscle cell, a mesenchymal cell, and an osteoblast. What happens is that these cells will receive different signals. And those different signals will change the gene expression in those cells. So they'll start making different proteins, and the cell will basically differentiate from one type of cell, often a stem cell, into a different type of cell like an osteoblast. So when a mesenchymal cell differentiates into an osteogenic cell, then an osteogenic cell differentiates into an osteoblast. What's happening is you are switching on and turning off genes, so you're regulating gene expression to cause these cells to change. Okay? Now, we've got osteoblasts inside this primary ossification center. Now, remember, in our flat bones, like the skull is a flat bone, right? It's basically a sandwich. You've got your compact bone on the outside, and you've got your spongy bone on the inside. So think like, you got some hard bread in between with some peanut butter in between, right? And this primary ossification center starts in the middle, and it starts forming the spongy bone first, okay? So, second part, we've got osteoblasts. We know what an osteoblast does. These cells are metabolically active. They start to secrete this organic matrix. Remember, and this organic matrix will then calcify. Because you remember bone, right? It's made up of this inorganic matrix called the hydroxyapatite, which is made up of calcium, carbonate, phosphorus, and other minerals. And it's surrounded by an organic matrix of various types of proteins like collagen and proteoglycans. Okay, so in our skull, we're developing, right? We've got this membrane, this mesenchymal membrane. And what happens is that certain regions inside that membrane become a primary ossification center. We're going to start laying down primary bone. That happens when the mesenchymal cells, they change into osteogenic cells, which change into the osteoblast. We'll call that differentiation. Okay? And then we start forming this primary bone, And these osteoblasts, they are starting to form, this organic matrix around that. We're starting to form kind of like this, well, not kind of, we're forming the primary bone, okay? Now, these osteoblasts will ultimately get trapped inside there, okay? When they get trapped, well, they don't get as much nutrients, and they further mature into an osteocyte. Now, osteocytes, osteo means, of course, bone, cyte means cell. These bone cells, they don't excrete as much extracellular matrix. They don't need to, but they do excrete enzymes and other chemicals to help maintain the osteo or the extracellular matrix of our bone. Okay, now we've got this primary ossification centers being formed, and we're getting this early spongy bone is now being formed. Okay, now remember our flat bones. We got the spongy bone on the inside. We start getting the trabeculae of these early spongy bones are starting to form. On the outside, okay, we have osteoblasts, and they are they actually come also from the mesenchyme cells, and they start to differentiate into the periosteum, okay, and this is going to start forming the compact bone. Remember, compact bone is on the outside. So where you've got the mesenchyme and the mesenchyme cells on the outside, they differentiate into osteoblasts, and that starts to form the periosteum. And the periosteum, okay, you've got the osteogenic cells. They divide to form osteoblasts. And the osteoblasts near the periosteum, they start to form the compact bone. Okay. Now, what happens next? All right, we start getting this early compact bone is formed. The osteoblasts around the periosteum. Remember, the periosteum is on the outside. That's that layer on the outside. They're secreting this organic mix. They're forming this early compact bone. Meanwhile, in the ossification centers inside, you're forming the spongy bone. Okay, and these things are growing. They're growing, they're dividing, they're adding extracellular matrix. Well, to do that, you need lots of nutrients. You need oxygen. So you also get blood vessels that are growing in there as well that bring in all the nutrients and oxygen these cells need to grow, divide, and of course, create the extracellular matrix as well. And then the blood vessels also carry away the waste from these cells. Okay. All right, so that's intramembranous ossification. And, I've had two kids here recently when they were born, and some of you might be parents or know of this, but what happens is, that a newborn, their head has a soft spot, like right there. And what's happening is that those larger bones of the skull, they are still ossifying. And so the fusion of the skull is actually incomplete in a newborn, and then it completes after birth. And it probably helps with birth and having the head be a little squishy to come out of the birth canal. Okay, and we call those fontanelles as well. All right. So endochondral. Let's go to the other type, endochondral ossification. So if intramembranous ossification occurs in your skull and in your clavicles, basically every other bone in your body ossifies through what's called endochondral ossification. Okay, I'm standing in front of my words here. I need to think about this next time a little bit. So this begins with fetal development, and it takes a few years for it to finish. But by about the age 7, most of it is complete. Now, instead of using a membrane that is your model, in this case, we use hyaline cartilage. Wow, we're replacing cartilage with bones. We evolved from cartilaginous fish, or at least our ancestor fish did, right? Pretty cool that those processes are still maintained today. Now, this hyaline cartilage is made up of cells called chondrocytes and chondroblasts, and it's also made up of cartilage. And I'm going to have to duck out of the way here. but you can see the perichondrium. The perichondrium is, of course, the layer of cells outside your cartilage. Hence, peri means around. Okay, that's pretty cool, isn't it? Man, I love making these fish connections. They're so fun. Yes, I like to go fishing, in case you were wondering. All right. So, endochondral classification. Okay, well, first of all, if this image on your right, you can see that's a developing bone right there. And you notice most of it is bluish. The outline of it, the dark blue outline, is your perichondrium. Okay, that's what laid down the cartilage, the hyaline cartilage, which is inside of it. And that hyaline cartilage in blue, that is the model that we're going to replace. We're going to replace that with actual ossified bone. And you'll notice in the middle, where it's kind of, like this, you start seeing what is called the developing periosteum. We just saw the periosteum, right? That's the layer of cells on the outside of the on the outside of the bone that starts laying down compact bone. Okay. So here it is. Ossification begins when the chondroblast, those are the cells that laid down the cartilage, the chondroblast differentiate into osteogenic cells. And those osteogenic cells, well, we know what they do. They divide and they become osteoblasts. So what's happening, what you're seeing in this picture right here, if we were to go back one slide, you can see most of this is blue. Most of this is perichondrium and cartilage. Now we're going to take a smaller look at it. You can see the chondroblasts. They change into the they change into the osteogenic cells. Then the osteogenic cells differentiate into the osteoblasts. This is, of course, occurring outside. And as this process occurs, the perichondrium becomes a developing periosteum. And we know that the periosteum starts laying down the extracellular matrix for the compact bone. Okay? All right, so there it is. That's how we're getting started here. You can also see that there are chondrocytes embedded in this calcified cartilage. So if you're starting to notice, whereas intramembranous ossification began with the spongy bone first, in endochondral ossification, we start outside the bone. So these osteoblasts, they're excreting this organic bone extracellular matrix, the ECM, and this early compact bone, the first part of it is called the bone collar. Okay? Now inside the bone, internal cartilage, that's beginning to calcify. Okay, so that blue inside our diagram, that's calcifying. Now, as it calcifies, it cuts the chondrocytes off from the blood vessels, from its blood supply. Now, you cut life off from a source of energy and nutrients, life dies. So in this case, the chondrocytes begin to die. Okay? And then on this, what you can see that on this picture down there, that that the dying chondrocytes is dying inside the cartilage, but the bone collar growing from the periosteum on the outside is growing as the osteoblast is laying down more compact bone. 3. Okay. Inside of our bone. We're talking about inside now. Osteoblasts are replacing the calcified cartilage with early spongy bone. And on the outside, the bone collar is continuing to enlarge. So we're laying down more and more compact bone on the outside. Now, we have primary ossification, which isn't very strong. It's not as calcified or mineralized. But eventually, we start getting secondary ossification centers. And this is the tips of the bone. So we got the diaphysis, which is like, if we were to look at our humerus, this long part would be the diaphysis. The bone collar would be right here. And secondary ossification is going to start forming in the epiphysis there. And you can see the top, we're starting to turn from blue to whatever tan color that is. We're starting to see the secondary ossification centers. Okay, now, inside, you start getting osteoclasts. And what they're doing is they're etching little holes. and they're allowing blood vessels to enter in to the primary ossification center inside of the bone. And of course, this is going to start forming, which actually make the bone, the osteoclasts, which is involved with bone reabsorption, and of course the osteocytes, which are involved with bone maintenance. So these osteoclasts, they're inside the bone. And what they're doing is, well, they're reabsorbing some of that calcified cartilage, and this is enlarging the medullary cavity. And the reason why it's enlarging this medullary cavity in like our femur or our humerus here is because it can then fill with bone marrow. And then as this is occurring, the remaining cartilage is being replaced by bone. And also in stage 4, the epiphysis completes its ossification. Now, if you look at this diagram, you'll notice that there's these epiphyseal plates. Okay, when kids are like, yay high, right? Their bones, when they grow into an adult, their bones elongate, and the epiphyseal plate is where those bones are going to elongate as they continue to grow and reach adulthood. And that cartilage will eventually be replaced. Now, the articular cartilage is a type of hyaline cartilage that will remain there for life. And that's the cartilage between your bones that helps your bones connect and rub past each other. And in fact, whenever people get osteoarthritis, they start losing that articular cartilage, and the bone rubs on bone, and it kind of hurts. Okay, so we're good here. So we got the cartilage in those two places. One is permanent, the articular cartilage at the tips of your bones, but the epiphyseal cartilage at the plates, that will go away as you grow into an adult. Okay. So just to clarify a couple words here, this epiphyseal plate, I just talked about it. That's where your long bones are that's where your bone is going to take place. So with people with achondroplasia, basically what happens is that their bones don't elongate. So a good example of that would be Tyrion Lannister. That actor Peter Dinklage has achondroplasia. And if you've ever seen those dogs with those absurdly short legs, they are bred for achondroplasia. And, that's kind of like, it's a vanity dog. It's kind of mean because those dogs probably have types of pain problems from having bones that didn't elongate correctly. Okay, we also have these articular surfaces. Articulate, moving back and forth. All of our joints are able to articulate, and that's why we have the articular surfaces. And those articular surfaces are covered by a hyaline cartilage known as the articular cartilage. And like I said, this is where bones come together, and it prevents those bones from rubbing against each other. And I like this image of this hand of a small child, where it's an x-ray and you can clearly see where the bones have ossified and the long bones, and then over here in the short bones, and these are the carpals. There's lots of these little bones right here that allow our wrist to articulate in many directions. You often don't see them because the carpal bones haven't completely ossified yet, which is interesting. And I have to go here. Going back to our fish ancestor, those bony fish first evolved about 420 million years ago, and then about 45 million years after the origins of the first bony fish, there were these fish called lobed fin fish that had muscular fins, thicker, and put more minerals in there to make them stronger. So that allowed our ancestors to evolve to live on land by making stronger bones. The cool thing is they didn't have to evolve a new structure. They just modified an existing structure, the fins. These are modified fins. And, 375 million years later, all tetrapods, which are mammals, birds, reptiles, and amphibians, have a general bone pattern of one bone, two bone, lots of bones. And like I said, even a whale fin has a humerus, a radius ulna, carpal women as they age. What happens is there's less mineralization in the bone. So as you have less mineralization in the bone, they become more brittle and they're easier to break. And this is a real problem because as you get older, you might be prone to more falls. And if you tend to fall more and you fall and break your hip, you're immobile. And unfortunately, when older people fall and break their hips, it immobilizes them so they're not getting exercise, and they often develop pneumonia within a month or two and die. It's sad, but that's a common thing that happens. So, yeah. Well, at any rate, one way there are certain ways we can fight osteoporosis. One is diet. Well, you also get it checked through a bone density measurement, and if you do have osteoporosis, a diet, change your diet with high in calcium. There's some medicines I believe you can take for that. But importantly, something that we can do lifelong is exercise. Even just getting out and walking helps, because I'm standing up right now. I'm walking. I'm putting 180 pounds of pressure on my entire, hip and all the bones in my leg. And that exercise, that's stress, not bad stress on your leg, but that will cause, here it is, the osteocytes to go, hey, we need more extracellular matrix over here. So they recruit osteoblasts, and basically you can increase the mineralization of your legs or of your bones to make them denser and reduce the problems of osteoporosis. So walking is good. And, my plug for exercise, of course, walking not only is good for osteoporosis, it's good for your mental health, it's good for your vascular health. It can help reduce blood sugar and control blood sugar levels and reduce the impacts of diabetes too. So walking is very, very, very good for us. And of course, you can also do weightlifting, where you do weight-bearing exercise. You put a load on your bones, and that will also cause them to help become more dense as well, which will help mitigate the effects of osteoporosis. Okay, so that's all I have for today. We're going to continue on with bone elongation and growth next week. So don't forget that homework 3 is already posted. It's only on chapter 6.1 and 6.2. Okay. So until next time, I will see you guys on Tuesday, and have a nice weekend and stay warm. I think it barely got up to 30 degrees out here. And you guys have a good weekend. Oh yeah, and I have to do my sign off. Stay curious.